Stars so bright in the sky. On Arizona nights they fly. Nebulae in colors rare. Galaxies beyond compare. Sky tour in the night so clear. Brings the universe near. Real-time wonders to see. Streaming light for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds. Stories of the cosmos told. Through the lens, a distant dream. Living real like a gleam. Far away, up so high. Across the stars beyond the skull. Through the lens, a distant dream. Living real like a gleam. Lift your eye up so high. Across the stars beyond the sky. Sky tour shows us the way. Every night a new display. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new.
Hello everybody, welcome to SkyTour live stream. It is me, Mark D'Antonio, with him, Daryl Mason. Hey Daryl, how you doing?
I'm good, Mark, thanks. How are you? Hello everybody.
I'm doing fine, thanks. I'm doing fine. We got an eye on the weather out there. As Daryl pointed out before we went live, there are some clouds out there which I had noticed. So we're gonna watch the clouds and hope that they don't interfere with us. We've had some good performance lately with the observatory, so we're not too concerned about having to close up quickly if something happens. We've been able to do that pretty well, and so we're going to continue and not jump into a worry mode at this point. I'm just doing a little housekeeping here. I'll be with you in 2 seconds. We're gonna turn this on and save it, and that should be good. Okay, so I want to welcome everybody here to SkyTour livestream. I want to say hello to anyone who's new. I see some old faces. I see some new names. We have a Michael with us. How you doing, Michael? Nice to see you. Make sure that you join our channel. It's free, and so are the images that we're going to take tonight, by the way. I also want to say hello to the other folks that got here. First of all, Tiffany Echo at the top of the list. Hi, Tiff. Great to see you. How's Michael? I sent him a message weeks ago, and I haven't heard anything from him. He must be really busy. JSCO is with us. Hi, JSCO. JSCO is a past equipment winner, courtesy of Tiffany and Michael Tarr, who is also known as Calibos. And we have, let me see here, we got, Stan at Two Rivers Observatory, who's currently doing some imaging of his own right now. He's imaging the elephant's trunk. That's pretty cool, Stan. And Karen Belmont's with us. I know Karen. She's a really wonderful person. Chris Mindfork is with us. Hi, Chris. How are you? Excellent. She's showing her coworkers the show. Fantastic. Yeah, we have a fun time, don't we? And, Daryl provides some cool insights, and I provide some insights, and we actually have a fun time. Nice of you to come. So, we are currently imaging Measure 22, which is a globular cluster. These are halo objects that orbit our galaxy. We've talked about them before. And as halo objects that orbit our galaxy, they actually plunge through the disk sometimes and then come back up. And sometimes, as far as we know, they may leave some stars behind if they get too close to some other stars or clusters, or they might drag some stars with them. Because this is a massive gravitational center right here. If you think about it, right? If we come up here and look, this cluster right here, this is a conglomerate of hundreds of thousands of stars. Their combined gravity, sound like Darth Vader, the combined force of the combined gravity from all these stars can actually be very powerful and act on other things. So if there's stars passing nearby, like this star right here, if this star was like not in the cluster and this cluster passed near it, this cluster and its mutual combined gravity here could drag that star in and pull it along. So my theory, which has yet to be researched, I believe, is that these clusters will actually drag stars from our galaxy with it and with them up to their new orbits and take them into this new orbit, or possibly gravitationally whip them out of our galaxy. That's another thing that can happen. So this is the image. We're taking an image right now. We've actually got 28 images. I'm only doing a 10-second shot here. But in 10 seconds in Sagittarius, you'll notice the sky is a little bit bright and has this dark line down here. What's that? Well, that's actually the enhanced guiding error that is caused by the fact that the moon is right here, and we're looking right here. Now, thanks to our filters that we're using, when we are looking at objects here, all right, and the field of view is this red box that you see here, all right, and we're going to synchronize so that we're here. Okay, this just sets our coordinates on all the instruments involved. Okay, as we're looking there, it's not too far away that we have the near first quarter moon right here. And so we're literally very close to the moon. So we're going to get some additional brightness, but our filters can knock out a lot of it. So much so that you can actually see some red nebula, faint nebula, amid the moonlight that's interfering with our shot. So once we get away from the moon a little bit, it'll be much better. Okay, so this is what it looks like now, and I haven't even run through a focusing routine yet, so I haven't even focused. So if I zoom in on this, the stars might be out of focus. We'll have to check. All right, let's let this solidify into a proper. Yeah, there we go. Yeah, they're slightly out of focus. You can see that looking kind of bigger and bloaty. We want those to be more pinpoint. So what we'll do is, now that you guys are all here, what I'll do is come out of here and I'll save this anyway, just because. And I've got Measure 22. It says so up there, M22 Globular Cluster, GC. And there it is. I'm saving it, and you'll see a green bar appear. It's saving the astronomical file format, and now I'm going to save the image format. Right? And that's a PNG file. So if you clicked on that PNG file, this is the image you get on our server. So you can go download that and enjoy all these pictures for free. And if you wonder where that is, and you go to skytourlive.org, Okay, we are a 501c3 nonprofit. We could always use your help with the Patreon. Join our Patreon, and if you could donate to us, that's fantastic. There's a one-time donation on our site if you want, or just go get the pictures if you want. And if you get on our website, you scroll down, and as you scroll down, you'll get to a point that says take me to cool pictures, and read the instructions, and it'll tell you how to get them. Now, it's taken longer than we expected, but we have a written application that we've written. Actually, Izabela wrote it. Izabela is in our chat many times, and Izabela has written this such that we have years and years of our data available to you in an app that will work on iPhone, Android, and on the PC and the Mac. And this app will allow you to access all of our data. You can go see, for instance, every time we photographed a globular cluster, any globular cluster, or any particular globular cluster, or any other object we've ever done. And you can actually download the separate ones. You could, when you download them, you can do comparisons. And for instance, Izabela found asteroids in some of the shots that we never knew that were there. And an asteroid in this shot would show up as looking like a star. You know, unless it was fast moving, it might look like a little dash because it's moving through the field. Really cool stuff. So you can wait for the app, or you can go right now as we speak. You can go right here to skytourlive.org, and right there, and read the instructions. Scroll down a little bit. You can get artwork if you want. We have a store. If you go to our Etsy store, which is going to be up there in the upper right corner, right up here, this store, SkyTour Shop on Etsy, has a lot of our wonderfully processed images that are on cups and mouse pads and shirts and sneakers even, big giant blankets. I mean, it's beautiful, and they look really nice. So that's the sales pitch for everything we do. If you find it valuable, think about it, and at the very least, give us a thumbs up and so forth. Tell all your friends. Just like Chris Mindforked in the chat said, she's in Vegas, and she's showing all her friends everything that we do, and it's so kind and so nice, and we thank her for that. So this is cool stuff. So we've got 53 images here that we've taken, and what I'm going to do is just save it one more time, and then we're going to get out of this, save it exactly as seen. And now within about 30 seconds, these images are going all the way up, then back down to the cloud, and they're going to come into our server and be on our server, which you can access from skytourlive.org. It'll be literally as close to live as you can get it. You'll see satellite trails in some of them because satellites will go through. So right now we'll end this. I know that this one is one of Daryl's favorites anyway. He likes Measure 22.
Oh, yeah.
Yeah. So we're going to go to our low light view here, and you'll notice the screen's going to kind of look a little bit green, and that green is of course our low light view. It's sort of like a finder, and we have one more element here. Let me bring this back here. This is our stellarium shot. This shows us the night sky, as I mentioned to you before. We have all kinds of things. We can show constellation lines. Okay, we can show the constellation art. Okay, we can show all kinds of things. We have the red boundaries for the constellations. It's really something. Okay, and there's our constellation art. So there's a lot of things that we can show here. And we'll be taking a trip up the galaxy here, but let's why not take a look at the moon here in a moment. But I'm gonna first focus. So the thing I'm gonna do is I'm going to unfocus my image for real completely. Right now it's actually more focused than it was just a moment ago, but do it again and kind of make the images bloat a little bit. See how they're fuzzy now? Okay. Now I'm going to go and start a automatic process to focus our image. All right, and you're gonna watch down here. You're gonna watch little data points, little triangles. Red triangles are gonna show up, and they're gonna make a curve. And that curve, at the bottom of that curve, that will be the point at which the best focus is achieved. And you're going to watch it get more and more in focus, and then it's going to go back out of focus. And then after it finds that optimum location, it's then going to calculate the exact position of that best focus position and then automatically go to it. It's actually quite a nice program here.
Autofocus mimics what you would do by hand, probably, if you were actually at the telescope. You focus a star by cranking on the focuser until you make that star as small as possible. That's when you know you're in focus.
Yeah, and sometimes it takes you going back and forth until one looks better. You think about it like when you go to the eye doctor says, what looks better, A or B? And then they might do it again. There goes a satellite, that's a Starlink. And so you say, let me see it again. You go back to A and then you go to B and they go back and forth. And they're honing in on a center point, the lowest part of the curve. And for us, that lowest part of the curve is going to be right about here. And if it doesn't get it the first time, it will the second time. I started it kind of early. I should have started a little bit later. But it may catch it anyway. And if it doesn't, well, then we'll do it again.
Looks like it's off a little bit.
Well, it should be right here. And that was an early start. So, yeah, I found it.
There you go.
So watch what happens now. So at the end now, it immediately refocuses the telescope for us. That was actually a feature that I asked the author to put into his program. His name is Robin. Yeah, fantastic job. And his program, it would do an autofocus, but then you had to tell the telescope to go to that position. And unless I'm misremembering, he put this in because I asked specifically for an autofocus routine. And I'm pretty pleased with how it came out. This is really, hands down, the best program out there. It's called SharpCap. All right, so now, here it is. So let's just do a quick 15-second shot of this. And that corresponds to 15,000 milliseconds, as you see here. All right. And then we'll go into our deep sky mode one more time. As we go into deep sky mode, you'll see the last image of it that we took. And as we zoom in, all right, you can see how fuzzy the stars look now. See that? Now watch as the new one comes in. It'll overlay this one. Watch this.
You didn't clear the old image?
Yeah, it goes over it. So now the new one, you see, and it's kind of hard to see because we have some color noise in there, which I'm going to get rid of right now. Watch this. Bang. Much better already. And then we come over to what's called a histogram, and we darken it up. We get rid of the black level. We do this, and then we get our color settings right. Okay. And you can see that our stars are way more focused. It looks nice. The blue is the induced color from the moon, but we still get some of the red nebula that's around us here in this region of Sagittarius. And I can actually come over here and drag our mid-level down, and when I do that, you'll see that a lot of the noise goes away. And look at that. Now it's looking really good. And we see the Starlink satellite that went through here. I can't complain too much, guys, because Starlink is delivering this to you tonight. You know, so. And Calabos, or Michael, who is one of our giveaway partners, he and Tiffany give us equipment to give away to folks. And Tiffany said last stream that this will be happening again, and that they have to just get on a schedule. And Michael actually works at Starlink for SpaceX, so that's pretty cool. Yeah, see, so now this is a much crisper photo. Now that said, I know it's only a few shots. It's going to be only 8 shots here, but we're going to save it. And you've already seen this, so we'll move on. All right, and we're going to save it exactly as seen. Again, in 30 seconds, it'll be right up there at skytourlive.org, and you can go grab it. I want to say hello to Alex Slattery, who is come in. He says, how has Starlink been working for you? Well, in the beginning, it was actually okay with dropouts at some points. But now, as Starlink has matured and more satellites have gone up, yes, our images have more satellite trails. However, the images also are uninterrupted. We actually have a pretty consistent data throughout the night. If something goes down, it'll be the remote connection between Connecticut, where I am, and Arizona, where that is. I'm literally 2,600 miles away from all this action. So somewhere out in the middle of the Arizona desert, a building roof has slid off. Okay, that's the roof here. It usually covers this. It slides off, and I do that from a program I've written, which is right here. I wrote this whole setup to actually do all this work. And then when the roof slides off, that program also allows me to connect and turn on power to the telescope and so forth, do a lot of the good housekeeping things. But Starlink is now very, very dependable now. So I'm very happy with it. At the beginning, it was touch and go, but because we were in a zone that was low bandwidth, and although we're still in a low bandwidth zone for Starlink, we've actually got really good performance right now, and I'm really, really happy about that. Okay, one more exposure, and then we'll leave.
Can you zoom in a little bit before you go?
Sure. You want to talk about the stars?
Talk about the cluster.
Yeah.
It's one of the first deep space objects I ever saw. Always been one of my favorites.
It is interesting.
It was December in 1981 when I got my first telescope.
Wow.
And I always say each globular cluster kind of has its own character. When we look at M4, it's got a bright line of stars down the middle, and this one, actually, now that we moved in, it kind of buzzed out some, but if you move out a little, can you zoom out some? You see there's kind of a dark shoulder on the right and a dark shoulder on the left.
Right here?
Yes.
And then right here.
It makes it look almost like a triangle in the middle.
I also noticed that we have these lines of bright orange stars in here. And this might be a cluster that has a number of red giants in it. I'd have to check and see officially. There's a database called SIMBAD, S-I-M as in Mike, Bad, B-A-D as in me all the time. But SIMBAD is actually the place to go to check out the types of stars in here and what they are. Good stuff.
I know globular cluster stars is a general thing. They're population 2 stars, some of the oldest objects in the universe. They're metal poor stars. They're mostly hydrogen and helium. They have very poor metallicity, nothing heavier. What spectral class do they tend to be, though? I know when we look at globulars and we see some red stars maybe starting to evolve off the main sequence, but as a general thing, what class of stars are globular clusters made of?
I think that a number of the stars are F and K, not O or B, but more like maybe some A's, but we've got mostly the F's, maybe G's, and some K stars. So it goes O, B, A, F, G, K, M. Okay, and the O's are the hottest and bluest, B's are the next, and they're still very blue, and then the A's are basically white. And then we have the F stars, which start to go a little whitish yellow, and then the G's, which are the sun, which are whitish yellow, tending toward yellow, and the K's, which are orange. And those colors signify changes in temperature. So after K comes M, and M is red. And there are stars that literally look like the sunset sun all day long. You know, at noon, at high noon, you have a sunset red star, and at sunset and sunrise, the star on a planet like ours would look absolutely crimson red because of the sunset. And the thing is, these red stars don't have a lot of blue light in them, but they have some. And when you take out all of it, then all you get is the purest red light, and the blue light is removed by the atmosphere. And that's why the atmosphere looks blue, because the light from the sun that's blue, because we have that spectrum of red, orange, yellow, green, blue, indigo, and violet. All that blue light, and at the end of that spectrum is taken out and scattered in all directions, and that's why we have blue sky everywhere we look. So that's why we don't see space during the middle of the day. If we had no atmosphere, we'd see the bright sun, and right next to it we could see stars, if you blocked out the sun. All right, but right now we don't have that capability because we have an atmosphere, and so the blue part of the spectrum would be blocked, and M stars don't have a lot of blue light, but some, and it'll get blocked, and the stars will look absolutely crimson on the sunrise and sunset side, but they'll still be red overhead, which is kind of cool.
When you see red stars, M-class stars, you could say there are 3 different kinds. Most of them are red dwarfs, little bitty stars that last a very, very long time. The second kind are red giant stars, which are stars evolving off the main sequence. And then you have red supergiant stars, which are really evolved off the main sequence and are good supernova candidates like Betelgeuse and Antares.
Yeah.
Most red stars are little tiny dwarfs, so
Yeah.
they. I was reading today about that planet. I think they found around Barnard's star. Barnard's star is a red dwarf star, I believe it, and this planet is several times closer to its sun, its star, than the planet Mercury is to our sun. And yet it's in the habitable zone, just because red dwarf stars put off relatively little energy, and if you want to live where Goldilocks does, between ice and fire, you have to get really close to the star.
That's right. And the thing about that is, and maybe Daryl was going there, is that these planets around such stars, and by the way, they're called red dwarfs because they join all the other stars in one particular snaky line that we see when we plot color against brightness. And that snaky line is all the stars that are fusing hydrogen into helium. That's what separates those little red stars from those giants that he was talking about. Once the hydrogen fusion process is done, because there's no more hydrogen in the core, well, then the stars would become red giants. M stars will not likely become red giants. It's kind of a interesting evolutionary issue with M stars, but we've never seen an M star die yet in the universe, and the reason is because M stars are so small, and M stars are so small that they are actually the dwarf stars, the ones that are doing hydrogen and helium, that they have been in existence since the beginning of the universe, and no single one of them has died yet, has ended its existence, because they have another characteristic, and that is they use hydrogen, right, to make helium, just like our sun. But in our sun, the core, which is about 20% the size of our sun, which is almost 1 million miles across, 865,000 miles, is fusing hydrogen into helium, but only in that core. The outer envelope of our star is all hydrogen, for the most part, but it's not used in the fusion process. It's just glowing because it's ionized hydrogen atoms. Okay, so you're getting this plasma, and it's glowing. All right, so you got free protons and electrons from the hydrogen atom just roaming around in this envelope. Now, all that said, in the core of our sun, that's the only place the hydrogen is used for fuel. But in these tiny M stars, that core is a lot smaller. However, the entire star is doing something called convection. It's like a boiling pot. The stuff in the core is working its way out, and the stuff outside is working its way in. And since the whole envelope of the star is hydrogen, the entire star is basically its own fuel source. In our sun, the entire star's fuel source is still in that little core that's 20% the diameter of the sun is. Right? So that problem, in our sun, we don't have that convection the same way. We have a radiative core. The radiation is pushing out, pushing outward, and only in the outer reaches of the sun's envelope do we get a little convection layer. But you have all the rest of the radius down into the core, and that's radiative envelope out to the convective outside. And that's what we have on our sun. So that convection can't mix hydrogen from out there down into the core to provide fuel. So that means our sun won't last trillions of years like these red dwarfs, but only billions of years. We get 10 billion out of our star, and it's halfway there. So, but stars that are massive, like he was mentioning, Betelgeuse used to be an O-type star, one of the hottest and bluest in the universe. But wait, Mark, it's red. Yes, once it stopped burning hydrogen, once it ran out of hydrogen, the core contracted and the star expanded massively from that superheated core, and the outer envelope of the star just bloated so big that if it was put where the sun is, it'd go out to the orbit of Jupiter. That's huge. That's from here to Jupiter in radius, and you got to double that for the diameter. So it's a massive star, right? But that outer stuff, that's all hydrogen gas in the envelope for the most part. None of that is useful to the core anymore. It never was, because it was always in the envelope. So stars have these discrete, I guess you'd say, segments where certain things are shells, where things are being fused. The core is hydrogen to helium initially. That's what that snaky line would be down our Hertzsprung-Russell diagram, it's called. All stars are there when they start out. But then when they use up the hydrogen, they move off, and they become the red giants. They become the red supergiants Darrell was mentioning. And after that's done, if the stars are like the sun's mass, then they'll never become supernovae. They'll swell to red giant twice in their life because of processes, and then they'll shrink in the end down to a white dwarf, about the size of the Earth. So that's pretty cool.
The red giants, on the other hand, where the red dwarfs can live trillions of years, why we've never seen one die yet, red supergiants last millions of years. Or those O stars that turn into red supergiants, they live hard and die fast, and they typically live millions of years.
Yeah, when you think about that, and we're going to go to an example of a sun-like star that died just now, just so you can see what we're looking at. You'll notice the telescope is heading upwards. Let's make sure this is going to give it to us here. It should. We're heading back into the darker part of the sky. Let me zoom out a little bit. Yeah, and as you can see, there's something that happens when you move your mirror or you move your telescope. There it is. The telescope has something called mirror flop. The mirror moves a tiny fraction of a single millimeter, and that knocks the focus off when you raise the telescope up high or raise it down low. So we may have to focus again, but that's okay. Okay, this object here, okay, and I want to talk about the supergiants that Darrell was just talking about. When you see those red supergiants, they started life not as red supergiants. The color is related strictly to their temperature. So when we see a red supergiant, it means that the outer envelope of the star is only between 3 and 5,000 Kelvin. Now that is a temperature scale, and you might say, how does it relate to Fahrenheit? There's a calculation to get it to Fahrenheit, but it's 273 less than Celsius. So basically, when you look at it, it's close to Celsius more than it is to Fahrenheit, right? So here we see this object here. This is called the Dumbbell Nebula, and I'm going to focus again, and it'll be for the last time, because now that the telescope is up, we won't need to do it again. But the stars started out as these beautiful O stars, hot and blue. Not these, but say Betelgeuse. And when Betelgeuse evolved, it ended up evolving and stopped burning hydrogen into helium, and then it had to start burning helium into carbon. And basically, stars are responsible for creating all the elements we see in the periodic table. So, when Betelgeuse started making helium into carbon, it was swelling into a red giant for the first time. And then, as it burns through the helium, once it's done with the helium, it will start to contract again and then start burning carbon into oxygen and swell again to a massive size. And that asymptotic giant branch state, in which that's called, after the main red giant stage, is the point at which we see a lot of strange things happen. Betelgeuse is there now, and at some point Betelgeuse is going to go supernova, because it was one of these hot blue, the hottest and bluest stars we have in our universe, an O star. And now it looks like a red giant. When it was an O star, its surface temperature was like 35,000 Kelvin. Now its surface temperature, as it's bloated bigger and bigger and bigger, and those outer layers have gotten further and further from the very, very hot core, that outer temperature now is down to 3,000 or 3,500 Kelvin. So 10 times less. So that makes it redder. So in the universe, hot stuff is blue, cool stuff is red. Just like a flame. The hottest part of a flame, when you have a Bunsen burner or a torch, okay, the hottest part of the flame is the blue part. And the coolest part is the orangey part, right? Same thing in the universe. It's a physics principle.
Isabella's here. Hello, Izabela.
Hi, Izabela. Good morning to Izabela. She's in Bulgaria. I think her ears were burning. I think she heard me talking about the app she wrote for us. Hey, Michael Galea. Michael Galea is with us.
I'd like to add one thing to what you said.
Yeah.
When Mark talked about the Hertzsprung-Russell diagram, the stars at one end are the O class.
At the left, yeah.
At the left, they're very hot. They're very bright. They're also very big. That's what makes them O-class stars, is they have enough mass that they burn, they fuse at such a furious rate that they only last millions of years. So you have, they're big, blue, and hot, and when you get down to the M dwarf stage at the far end of the diagram, they're small, red, and cool.
Yep. Now, when he says they're big, he means it, because those blue stars at the end of the Hertzsprung-Russell diagram, that was it was Henry Norris Russell and Ejnar Hertzsprung who discovered this relationship between stars. The bluer and hotter they were, the farther left on the diagram, the color, when he plotted color of the stars versus their brightness, which we call luminosity, they found that there was a snaky line that developed. And those stars were the ones that were doing normal hydrogen fusion, hydrogen into helium, the first stage. Okay? Now the process by which they do that, it differs for the mass of the star. There's two kinds, but we're not going to get into that. All right? But the fact is, when you look at these very hot blue stars, as Daryl pointed out, they don't last a long time because they're so fast and furious the way they burn through their hydrogen that in just a few million years, as he said, these stars will go through all of the hydrogen in their cores. They don't have that convection we talked about with the little red stars, which do all of that. They actually are all radiative to the outside, all right? And there might be a small convection layer as the stars get a little cooler. But in the O stars, they're radiative. They radiate outward all this energy, and it's only in their core where they're actually fusing anything to anything. Nothing in that outer envelope. That outer envelope is just a hot location, all right? And it's much cooler than the core, by the way, even though it's already glowing hot, okay? So the point is, those beautiful red stars end up becoming, those beautiful blue stars end up becoming red stars, because as they run out of their hydrogen, they will swell into those red giants. And the farther away from the center, as I mentioned, that the radius that the outer envelope gets, the farther out it gets, the cooler that gas will get, and the color will change appropriately. It's like heating something up to white hot and then letting it cool. As it cools, it changes color. It'll go from white hot, from blue hot to white hot to red hot. Still hot. And then finally it'll fade to a color that's just barely red, and then that'll go back to the natural color of the metal eventually. So that's how that works.
Stars like this, on the other hand,
Yeah.
this used to be a sun-like star, roughly the size and mass of our sun. Might be a little bigger, not too much bigger. Once it gets old enough, it sloughs off its outer layers and becomes a planetary nebula, which is what this is called. This is the Dumbbell Nebula.
Yeah, and planetary is just a moniker, though, as you were saying.
What was left of this star, what was left of it became a white dwarf star, which we may see down in the center. White dwarf stars are much tinier than the suns that came before them. Mark says about the size of the Earth, and yet we can see it from hundreds of light years away, as small as it is, because it is so incredibly bright, the white dwarf. And it's mostly radiating in, a lot of the radiation is ultraviolet, which is what is making the gases in the nebula give off various colors of light. You see the blue there, that's doubly ionized oxygen. You see the red, that is mostly singly ionized hydrogen.
That's the hydrogen.
And those are the layers that that star puffed off when it went into the process of turning into a white dwarf.
Yeah.
And we call those planetary nebulas because they look sort of like planets in the eyepiece.
And now if you look in the center, right here in the center, you can see that little tiny dot. Now, from several thousand light years away, literally, you're seeing an object the size of the Earth. But that doesn't seem to make sense, does it? Because it's like, how could we possibly see something that small from that far away? You could, if this little tiny point of light was brighter than almost anything around it. And that's what we're seeing. We're seeing an object that's exceedingly bright. And that's what makes a white dwarf what it is. A white dwarf is the stellar remnant of a star that once was. This is that stuff that was in the outer envelope, the stuff beyond the core. The core of the star is contained within that little white dwarf that we're seeing right there. But it's ultra compact. If you took a cubic, a sugar cube of this material, a sugar cube of white dwarf material, if you could take it out of that star and somehow weigh it on the Earth, it would be as heavy as a car. Okay, 2,200 pounds, about the size of a sugar cube, okay? Now, beyond this, if the star was more massive, then we wouldn't see a star if it went to a black hole. However, if it didn't quite get to a black hole, which is from a massive star, and it was a star that was maybe 3 times or 4 times the mass of the sun, and not 20 or 30 times the mass of the sun, then we'd get what's called a neutron star. Now, in the white dwarf stars, they're very compact, and most of the nuclei in these are carbon and oxygen on the surface. Very, very tightly packed together. Think of a checkerboard where there's something in every single checkerboard square, and you can't compress that checkerboard square anymore. You can only have one thing per square. Well, the next step with a more massive star is the neutron star. And the process that makes neutrons in these heavier stars is called neutronization. Go figure. And when these neutrons are made at the point where the star has gone supernova, the neutron star, again, very, very dense. Again, think checkerboard, where every single square is filled, but make the checkerboard squares twice as small or 5 times as small as they were with the other checkerboard, and then fill every square. Much more compact. How much more compact? That same sugar cube of material, which if you could theoretically, and Daryl may tell you why after this, if you could theoretically take that sugar cube of neutron star material out and weigh it here on the Earth, it would weigh 467 million tons. Quite a difference from 2,200 pounds, which is 1 ton, just over 1 ton. So 467 million tons. Okay, that's or 467 million pounds. So that's actually, no, I was right, 467 million tons. So that's actually quite a heavy cube, and that's how much more compact a neutron star is.
And as Mark warned you, if you did take that teaspoon or sugar cube, whatever, of neutronium out from the confines of its own gravitational field and opened it on Earth, well, you would get an explosion like you simply would not believe. It could probably wipe out the whole planet.
I would think that's probably true.
Because the gravity of the neutron star is the only thing holding those electrons and protons into compression into neutrons.
Yeah.
And it will disassociate explosively if that gravitational field is no longer constraining it.
Yeah, and the reality is, as Daryl said, there's no way we could actually do that. But again, it's a thought process, so you can actually see a thought puzzle. You know, if you were to be able to take it out, it would these little sugar cubes would weigh that much from a white dwarf like this one, the size of the Earth, or a neutron star, which, by the way, a neutron star is about the size of Manhattan Island. So quite a big difference from the size of the Earth, with a mass of about a little just below the mass of the Sun in it, to the size of Manhattan Island with the mass of even more in the center, because those are stars that are just around 2.4 times the mass of the Sun minimally. So there are some pretty interesting anomalies that can happen with neutron stars. Some neutron stars will have hot spots on them that actually flash like lighthouses because they tend to spin rapidly, and they're very, very highly gravitationally bound. And so most neutron stars are rapid rotators, probably from the tumultuous and catastrophic manner in which they were formed. So when that happens, there are neutron stars that can spin at around 30 times per second, as in, say, the Crab Nebula in Taurus. That Crab pulsar is a neutron star that's rapidly spinning. I think it's 33 times per second. Imagine a whole star the size of Manhattan Island spinning 33 times per second. Wow, that's the whole thing going like this, 33 times per second. And the gravity is holding it together.
Some neutron stars spin 1,000 times or more a second. They're called millisecond pulsars.
That's right. That's right.
And imagine spinning 1,000 times a second.
At the size of Manhattan Island. You measure the rotation rate not in, rotations per second, but in a frequency, because it's almost like a frequency. It is a frequency that you're measuring it in, because it's going so fast. This star death is actually a very gentle star death, because this process didn't happen catastrophically like a supernova. This actually happened rather benignly over a longer period of time, because, as we were talking about earlier, this star, and I'm going to be processing a little bit to show you this, started sloughing off its outer layers. And so, like, the star started pushing off this little guy right here started pushing off these outer layers, and you can see some beautiful loops here. You also see some interesting arcs out here of more material That's interesting because that shows you that this material has been pushed off from way earlier in its evolution, or that might have been material that was pushed off more rapidly than the earlier material in here, and so it may have outpaced the other material. Depends on the processes. The other thing to keep in mind, this is something Daryl and I have talked about as well. When you look at the star, you want to draw like a logical axis, and this, like through the center, if we go through the center of the star like this, okay, if this is the North Pole, this would be the South Pole. We might think, well, it should be this way, right? Well, actually, the star might be rotating, and if it's rotating, it's largest at the equatorial regions. It's going to be oblate. It's not going to be a round. It's going to be an oblate spheroid, and an oblate spheroid will be bigger at the equator. And so, as it's spinning rapidly, it might actually be spinning in such a way that the gas would be forced outward this way. And notice this shape here. It looks like an apple core, as we've talked about. This line right here looks like a hot spot, and it makes a line right through. And I'm going to draw a couple more lines to illustrate another potential thing that this could be doing. And we're going to go like this. Okay. And then we're going to go like this. Okay. Through here. Okay. Now, if you look, this is our north and south. But this might have been north and south, and this might have been, this might have been north, and this might have been north. It could be that what was going on, or what's going on here, is that the star is actually precessing and kind of moving in a circle around that point, doing this kind of thing, like a spinning top. And as it's doing that, maybe it's expelling stuff along its region here and down through here. Maybe this is the reason why this is called a bipolar nebula. In other words, two separate pole-looking pieces here. Now, this is my theory. I haven't seen this officially, but I do think that there's merit to it. So I'm gonna look into that as well and find some more studies on the Dumbbell Nebula. But it's quite a fascinating location. Now, the other thing, too...
Marianne is here. Hello, Marianne.
Oh, Marianne is here. I didn't know you'd have signal down there. Oh, yeah, service is very poor. She wanted to say hi. Well, thank you, Marianne. Marianne is the second of three in our 501c3 nonprofit organization. She is Marianne Robb and joins us with Tara Diulis, who is the third person. And then there's me, the big mouth at the front. Well, anyway, that's cool. Thank you for coming in, Marianne. Good to see you. Hey, Ron Regier is here. Ron is cool. If you know Ron, say so in the chat. Ron is really cool. You know, he's done some forays to the Grand Canyon, looking for special areas there on Indian lands that might actually hold clues to ancient archaeology and visitation. It's really, really neat. And I still want to go, Ron, on an expedition there and do that. I want to say hi to Hein Cherry. How you doing? Hein, where are you from? Okay, and then Mr. Django was here before. He's from Belgium, joining us early in the morning. He probably fell back asleep, but shh, don't wake him up. Ronald from Hurt Radio is with us. How you doing? Michael Hedrick's with us. How you doing, Michael? Yeah, so we're up to 36 shots here. That's more than enough to get a really pretty dumbbell nebula here.
May I?
Yeah, please.
Digress a moment.
You may.
Scroll back out on that.
Okay.
Make it smaller.
I'm sorry. Let me get back in there. I was on the wrong thing. Okay.
Maybe about like that.
Okay.
Now take the color out of it.
All right. We can do that.
Please.
Yeah. We'll drop the color now.
This is another one of those objects that some of the first things I ever saw, deep space objects, when I got my first telescope. When you look through the eyepiece of the Dumbbell Nebula, perhaps you can see why they called them planetaries. You don't see any color in a small telescope, it's just gray, but it looked to me almost like a ghost of the planet Earth. Those two lobes you're looking at now, they looked almost like North and South America in the eyepiece. And it looked for all the world like the ghost of planet Earth floating out there.
It does, look at that.
And that's why they call them planetary nebulas.
That's very cool. And depending on the telescope you have, you might see it like this, okay, or you might see it like this, which is coming in maybe a little even lower. You know, depending on your telescope, you might just see a hint of this. But in reality, the way it works, it probably end up like this. Okay, you'd probably see some of this, but that's black and white, and we actually have the ability to run in color, which we really like. Okay, now
you can also see why they call it the apple core.
That's right, because of that shape, yeah. And what you do, another trick, again, when I was getting my degree in astronomy, we did this often. We actually used charts that were actually negatives inverted. So we had charts that looked like this, okay, except they were in black and white. So for instance, the Dumbbell Nebula would look like this right here. And that's actually precisely, almost exactly what we had for the dumbbell in particular. I actually have one in the back room, one of the charts that we used. So why would we use negatives? Because sometimes you see more subtle detail in a negative than you do in the positive, right? So when we jump out of the positive, you might miss some details in here that might be faint, but in the negative you can catch them. And we'd go back and forth, and it's pretty cool. Now keep in mind that we were using photos from the Deep Sky Survey and the Palomar Deep Sky Survey and other sources from around the world. So it's pretty neat seeing all these different flavors of the same object. And as you see, we're doing it right now. We got them. Really nice. Okay, we'll save this. And then save it exactly as seen. Now, I didn't look in the chat, but in case you asked about the colors, this bluish color here, this is the color of ionized oxygen, but it's doubly ionized oxygen. Oxygen has several electrons available to be ionized on the outside of its orbits, and if two of those electrons go out, when they come back in, they give off a little bit of light, and that particular light is blue. When something's ionized, when the electrons lose some energy, they'll fall back into the atom, and when they do, they'll give off the light. That's where this is coming from. Hydrogen does the same thing, but it only has one electron, so it only has so many places it can drop to. The predominant one is red, and it makes a red color, and that's what we're seeing here. There's more oxygen here in this particular part of the nebula, thus we see mostly the bluish green color and not the red. If it was hydrogen dominant, this would all be red. So pretty cool. Hello, Cindy Murphy. So neat.
When you see planetary nebulas like this, because of the nature of the stars they came from, middling size, maybe like our sun, maybe a little bigger. Well, what's left, the white dwarf, it's giving out a lot of energy, but it doesn't give out nearly as much energy as, say, a neutron star. And therefore, they tend to be within a certain range of sizes. And planetaries might be a couple of light years across, and that's about it. You can faintly see an outer shell on this to the left and to the right. I posted that apod pic in chat, Mark. That is a very deep exposure from a very large telescope, and it shows tons of detail, and it may even show those axes that Mark was talking about.
Okay, let's see if we can coax a little more out by doing this. Okay, now let's actually do this. See if we can get some contrast.
Yes, Karen, it's mostly hydrogen.
So you
Maybe
got,
a little bit of neon in there too, which is also red.
yeah. Oh, did she ask if the red was hydrogen? Okay.
Yeah.
Yeah, it's in a star-rich field too because it's in the Cygnus star cloud almost, and there's a lot going on up here. So that's pretty cool. I'm going to drop us back down, and now it's interesting. With a camera, we can see all this color, but if we're out there in space, this would actually just look like a gray cloud to your eye, and then once you got closer to it, you might not see it at all. Even our solar system right now appears to be embedded in a nebula, but we don't really see it because we're inside of it, and it's not very dense because we're in it, meaning that the atoms are very sparse. They're very widely spaced. You might get 30 atoms in the size of a sugar cube in interstellar space in one of these nebulae at the most, but here on Earth we've got like 10 to the 20th atoms in a cubic centimeter, a sugar cube of air. So the density is incredibly different, going from 30 atoms to 10 to the 20 or so atoms. That's a huge difference. So on the Earth, density is increased by millions, okay? And that's the thing that about the universe that we don't realize. If you got in this, you might not even know you're in it. You might notice that the temperature on the outside of your ship started to increase because the radiation from the white dwarf was striking the outside of your ship, heating it up, because your ship would absorb radiation. But the atoms are so far apart in here that the atoms wouldn't heat up your ship. The radiation from the white dwarf would heat up your ship. So again, really interesting details about the reality of traveling out there. But let's get in here real quick one more time, and there we go. And now what I'll do is I'm going to I'll take down the central brightness a lot so we can see that white dwarf in the middle right there. There it is. That star is between 30 to 35,000 Kelvin. Very, very hot. It's the size of the Earth, as we said, invisible being a couple thousand light years away at least. So that's not bad at all. That's a very, very bright object. Okay. Well, we're up in Cygnus in that region. This is a beautiful little guy. I'm going to actually save this like that. That's 60 images. And I'll save it just like it is because it's pretty. I actually had a print of the Dumbbell Nebula like this. It was about this big. And I had it on my wall for a long time. Everywhere I'd go, I'd put it up on the wall. It was really cool. But it was taken with a professional telescope. And I have to say, ours is better. It really is. You know, it's pretty cool. Alicia Vieras, hey there. I saw you here earlier and I didn't say hi. My apologies. I'm sorry. And Walter's with us. Hey Walter. Walter Kokubinski. How you doing, man? Nice to see you joining us tonight. If you haven't subscribed, please do. It's a free channel, and this photo, like you see right here, free. You can take it, do whatever you like with it. Okay? If you join our Patreon, you can get highly processed versions, higher resolution, and they're just beautiful as prints on canvas. We have that availability too. You can get those through us if you want. A lot of people have done so. We have a connection to Darkroom, which is what allows us to do that. Just beautiful. Okay. All right.
Would it be logical to sort of jump to the next level and go to the crescent?
Yeah, because that's a great idea, because that's the next step to supernova, isn't it? This is the end of star life here. And Daryl's mentioning the crescent. And then we'll go there next. The crescent is an example of another star type that's out there. And then we're going to end up going to the veil too, because I think the veil will also show the final stellar end of existence state.
Sounds like a plan.
Yeah. Okay.
Where we just saw the dumbbell, a planetary nebula. It's put off by a roughly sun-like star. If we go to the crescent next, we're going to see what happens when a bigger, hotter star puts off a nebula. It's not called a planetary anymore. It's called a Wolf-Rayet nebula. And that's because it comes from a Wolf-Rayet star, which is a huge, furiously burning star getting near the end of its existence. And it's puffing off all sorts of material also, but it's a much, much more violent process.
Yeah.
And it's a lot bigger than a couple of light years across.
As we move into winter, there's another one of these Wolf-Rayet nebulae that we'll be able to view as well, and it's just incredible. That's Thor's helmet.
Yeah.
I've never viewed Thor's helmet with this camera, so I'm really looking forward to it. It's going to be much more detailed.
Surely we have, haven't we?
This telescope camera didn't come along at the right time. I don't think we've ever done Thor's helmet with this camera.
I thought you had this camera running by the time last winter came around. It was summer stuff.
It might be.
That we hadn't seen before
Maybe,
with this camera.
maybe, yeah. By the way, there's two things to point out here. By the way, here's the Crescent Nebula. We're gonna photograph that. Okay, that star Daryl's talking about is right here. Wolf-Rayet stars are much more massive stars than the sun by 20 or so times, and as he said, they're very furiously, burning, fusing in their cores. The thing is about these stars is that they have very, very powerful stellar winds. You know about the stellar wind from the sun when there's a cosmic, a coronal mass ejection. It's like a cosmic catastrophe. It's sending all this physical material off the star out into space, hits the Earth, causes aurora borealis in our sky, and we see northern lights. Woo, looks beautiful. What's really going on is a massive catastrophic explosion off the sun, sending chunks of itself out into space. Multiply that by 1 billion times and you get the power output of a Wolf-Rayet star. This star sometimes most of these Wolf-Rayet stars are so powerful, their stellar wind is pushing so much stuff outward that their entire outer part of the star around the core is being pushed away from the star. Now there's a certain point in the star's evolution where that becomes very possible. And that's at that asymptotic giant branch, the second time the star goes to red giant. And don't worry about that, but just understand that there's a point in its evolution where it becomes very easy for those outer layers to get separated from that core, and that's what we're seeing here. Now that core is still furiously fusing as best it can, but it's going to run out of its nuclear fuel sooner than later because it's so massive they burn through their fuel very, very quickly. So this star right here, it could go supernova right now as we watch it. We don't even know. All right. Now this star up here is kind of different by quite a lot, but that little red star there is a fascinating star because this is a carbon star. This is a star that is it's in that same point in its life, that asymptotic giant branch, but it's dredging up all the carbon that was created in the core and pushing it outward into the outer atmosphere of the star. And it goes so far away because it's such a big supergiant star that the carbon actually can bond to each other and make molecules. You can't have molecules above a certain amount of temperature in a star's gaseous envelope, but in the way outer reaches of these big supergiants you can, and that's what we're seeing here. And so the star looks blood red many times, and we'll see that in just a second as we do an exposure here. We're going to do a 25-second exposure, okay, and we're going to go into deep sky mode. All right, so we're going to drop out of this. You'll notice that our carbon star is still visible, but we don't see our crescent yet. So when we come into the live stack, the last thing we shot is the dumbbell will be there, and we're gonna clear it because we have already saved it. That's already up on the server as we speak. Hey Sam S, hi. I didn't say hi to you earlier. Okay, so there's the crescent, and there is that carbon star near the crescent. I think that's just beautiful. We looked at carbon stars the other night, actually. So I'm gonna just do a color correction, make sure we get the right colors. You'll notice the change, but you notice that in that color change, you see all this red nebula now around here. And that's with the moon out. We have pretty good filters on this telescope. So right now, we can do some processing to show this better. Okay, you'll notice it get brighter right now. All right. So this is our dark level. As long as we don't pass the average curve peak, which the average of the red, green, and blue is this white curve here. So as long as we stay just to the left, then we won't lose detail. And we'll color correct. We keep color correcting along the way. All right. You'll notice the red nebula showing up. You notice the carbon star showing beautiful red. You look at this. Here you can see this incredible and mostly complex nebula. Again, the outer layers of this star being ejected by the star's massive stellar winds. Deadly
Good night,
location.
Marianne.
Was she leaving?
Yes.
Oh, let's see.
Good night, Marianne.
Oh, yes, she's right. There you go, Marianne. Good night. Yeah, she's got an appointment with our potential next site for all our telescopes. It's a professional site. It's going to be really nice. We'll have complete access to it. Look at this beautiful nebula, guys. Look at this. So the Wolf-Rayet star here is destined for supernova. There's no two ways about it, and there's no getting away from it. It's going to burn through the rest of its nuclear fuel at some point, and then just obliterate itself. And it might even destroy this nebula it's made when that happens. Wow.
So you see this, and it might look like a planetary nebula, but it's not. Well, again, they call it a Wolf-Rayet nebula. I've been meaning to try to hit up Mark about past things I've read about Wolf-Rayet stars. I think they said that some actually are associated with planetary nebulas, but only certain types, and only certain types of star, of which are several different flavors of Wolf-Rayet.
That's right, yeah.
But as Mark said, you're probably looking at a star with a mass of 20 or 30 times the sun, and it's much different processes going on, and what's coming off of this star is much different than what's coming off a planetary nebula.
Yeah.
Or off the white dwarf of a planetary nebula.
Right.
And
go ahead. Sorry.
This is going to wind up being a neutron star or a black hole.
Yeah, depending on its mass. You can have a neutron star up to, again, we give a mass. We're talking about the mass of the core only. We're not talking about all the mass that was lost. This star is also losing lots of mass. It's pushing stuff out, right? Well, if the core itself is about 2.4 times the mass of our sun, then that's about the upper limit on a neutron star. But if it becomes like 3 times the mass of our sun in this little core of this star, then when it finally does contract, it can actually contract past neutron star stage and become the black hole. But it's, again, I don't know what the mass in this core is, if there's been any studies on it yet. I know there's studies, but I don't know what it might have said about this. That's actually beautiful, though.
Looking.
And now if I'm going to drop down here just to show you here's our beautiful carbon star up here.
This is 5,000 light years away from Earth.
Yeah.
When we looked at the dumbbell, I believe it was 1,200 light years away.
Yeah.
This was discovered by William Herschel, unsurprisingly. Blah, blah, blah.
I'm going to do an annotation too, guys. Now, we can actually have this identify what we see in the image here. Okay. And here you see it. Here's Crescent Nebula as defined by our annotation. We're going to save this image with that annotation for you. So that will be available as well on skytourlive.org. Okay. And so those are there. It didn't know about our star here, but we can actually come into our planetarium, and we are at that location where the Crescent Nebula is. And because this red square is the size of our field here, so we zoom in. Okay, you'll notice that it's a little bit on an angle here, and it's upside down. And so I'm going to actually synchronize, so make sure that our telescope and the stuff is set up same way. And now up here,
Crescent is 25 light years across,
okay,
compared to 2 or so for the dumbbell.
so if we look at this star, this is the star we're talking about. It's known as BLL 47 or RS Cygni. The Hipparchus designation is 99653. The Henry Draper catalog number is 192443. The Smithsonian Astrophysical Observatory catalog is 69636, etc. And now we look at its spectral type down here. You'll see a spectral type you may not recognize. It says C-N5.5. What? That's a carbon star. That's what the C is. And the N is, it goes back to our Hertzsprung-Russell diagram. We talked about OBAFGKM as our stellar classifications. However, it used to be that we used to talk about R, N, and S at the end of that. And the N stars, these were, the RNS stars were carbon stars. They ended up getting their own designation. So you have these, the carbon stars, and then we have the N star here. This is 5.5. So you can get carbon stars, you know, that have many different levels of carbon in their outer atmospheres, and that would determine what we're seeing here, would determine what spectral type we would actually call this. Now we have 17 shots here, all looking beautiful. We're using a full width half maximum filter. As you can see here, every one of our shots have been successful. It's a very calm night right now, and we have our telescope sticking way out of the top. Let's go look at our all sky camera and check on the status of our clouds. We have the moon is down here. The clouds that were out here are gone. This is a reflection, a lens flare from our bright moon down here, as is this, centered around the middle of the lens. It's a dome sitting out there. And this light out here is Phoenix. That's around 80 miles away to the east. And then we have nothing. If there's clouds in the air here, right about here, they start getting dark. They look black to you. Over here, you'll see them lit up by Phoenix. Over here, they're black. Okay. When the moon is very bright, the clouds will have a brightness to them. But this is our Milky Way, our summer Milky Way. We can see with our constellations, we can bring up our constellations. And we see Deneb, which is in Cygnus of Swan. And this is where we are right now. We're actually looking right about here in Cygnus, and we're looking at the nebula that's right about here in Cygnus. This is Deneb, this is Satyr, and right about there is the Crescent Nebula. And then we have Albireo down here, which is this beautiful double star. There's Lyra, okay, and then we have down here, we have Altair. So in our night sky, one of the things that we talk about, Daryl talks about it, I talk about it, we talk about the line from Deneb to Vega, and then from Vega to Altair, okay, and then from Altair back to Deneb. This is what we call the summer triangle, and this represents the stars of summer for us. Now Sagittarius is down here, out of the view down there. But yeah, so there's your summer triangle.
Django asked about your all-sky camera.
Oh, he did? What did he say?
He said, Mark, did you make any changes on the all-sky camera?
Oh, no, I haven't. I didn't change the exposure. I'm doing 15-second exposures. I'm having it do auto, as you can see here, 15-second auto. If the bright moon comes out, it'll drop that exposure a little so it doesn't blow it all out. So yeah, no, nothing's changed.
Can you draw the leg from Vega to Altair again?
Yeah, I can do that.
Of the summer triangle?
Sure. So here's Vega right here, and here is Altair down here. And
now then, if you go from Vega toward Altair, not quite halfway, there's a fairly bright star just a little bit offset to the left in that image. And that's Alberio, which is the head of the swan. Cygnus is a swan.
Mm-hmm.
Just up a little bit, Mark.
No, you're talking about here.
Yes, that's
Yeah,
Alberio.
Yep.
That's one of the most beautiful double stars in the sky. And if you can put the constellation back,
Yep.
when you see Cygnus, Deneb at the top, Alberio's at the bottom. Deneb is the tail of the swan, and you can see the two wings coming off to either side. And Alberio at the head of the swan. That also makes the Northern Cross. Deneb is the tail of the swan with the head of the cross. Alberio is the head of the swan and the bottom of the cross, the foot of the cross.
Yep. Cool. Yeah, so we checked this, and we don't have any weather to really worry about here. We've got Milky Way. We love that. We don't have any fires to worry about out there. We've had those before. So look at this. 27 shots in. Oh my, 28. That's beautiful. That's a stunning photo. And if we zoom out a little bit, you can really capture the full majesty of the nebulae that are around this. You're seeing this live, guys. This is live from the Arizona desert. You know, I'm in Connecticut. This is in Arizona. And we're running it from here. It's beautiful. Go ahead, Daryl. I'm sorry.
Karen asks, is there not a black hole in or near Cygnus? There's a bunch of black holes in Cygnus, Karen. There is Cygnus X1, which was the first black hole discovery. We've identified it in some Cygnus pictures before, I forget which one. There's Cygnus X5, I think Mark says.
We'll see that in a minute. Not really, but you know what I mean.
Yeah,
right?
It's the progenitor of the Veil Nebula.
Yeah, which we'll see.
When we're looking up toward Cygnus and Deneb, we're looking up into a very star-rich area. It's like in the next spiral arm over from us, and there are oodles and oodles of stars, and lots of big ones, like this Wolf-Rayet star we're looking at now. And there are probably many black holes, more than you could shake a stick at in the Cygnus.
Oh, I bet. Yeah.
We can't see them, but we know where they are. Some of them.
Yep. Okay, so here's the image that is saved at skytourlive.org. When you go out there and go to our server, here's the image that you can download. Isn't that beautiful? I mean, talk about making a beautiful background on your computer and everything. This is what you can do. Take it down. Enjoy. All right. So, this said, this is a region of space you never want to go to. Not that you ever could, but if you actually could, then you can be sure that you're gonna just melt your face off. This is an extremely hot region. Radiation from this star will literally disassociate the molecules in your body rather rapidly. Next lady's with us. That's Kathy Prunasek. Hi, Kathy. How are you? Nice to see you. Thank you so much for coming out and saying hi to us. This is cool. Alright, yeah, so something else that's rather interesting, Daryl, that I didn't notice before in the crescent images we've taken is this dark nebula in here. This looks like a dark nebula. I haven't seen that before.
I'm sure it's always been there. We probably just didn't notice it.
I know. Let me just bring this up a little bit.
That's cool.
Alright, this is really pushing things to try and see what's in here, guys. Look at that.
I see a dark wavy line coming up to from the bottom left corner.
Up here?
Right there, yeah.
Yeah, look at that. Yeah, and again, you'll notice that it's not empty, is it, guys? Space is not empty. There's plenty of things going on here in the universe. A lot of stuff that we just don't realize is out there, and only through a long exposure with a camera can we possibly see this stuff. Okay, and if you use a regular telescope and just looked at something, if you looked at the stars here through the telescope, you'd see no hint of this red nebula with your eye. You have to take it with a photograph. This is faint, diffuse hydrogen that is glowing, caused by stars in the region ionizing the hydrogen gas. Fantastic. Okay, we're going to take this photo and move on to the next thing. So, we saw the Dumbbell Nebula, which is a nebula, the Blue Nebula, which is a sun-like star. We're seeing here the coming end of a star, and that was the end of a star like the sun. This is a nebula that precedes the end of a star that's much, much more massive than our sun. It's not a common occurrence, though. Wolf-Rayet stars are not very common, but when they're there, they really, really are blazing beacons in the universe, and this is the case where we're seeing them. We saw this star here, which is a star that's not a Wolf-Rayet star, but it's a star more massive than our sun, and it's made a lot of carbon in its outer atmosphere. The end of this star could end up being a white dwarf if it's a smaller mass, or a supernova if it's a little bit more massive. I'm not sure about the mass of this star yet. I'd have to find out. All right, but if there has been a supernova, one of the things that we would see, and I'll save at 40 now, is the next item that we're going to look at. And you'll see the kind of debris that's created when a star finally does blow itself to smithereens. Stay tuned. We're going to be right back after this commercial break. I've always wanted to say that, but I don't have a commercial. I'm just kidding. All right, so this image will be up there in about 30 seconds for you to go check out. All right, and after that, we're now going to go to our low light view and check out this next object. So let's go here to our stellarium, back out a little bit. There's the crescent, and we're actually heading out to the edge here of Cygnus. This area right here in Cygnus is going to be a little bit more above us. If we look at our zenith values, this is the zenith up here, this is the zenith. These coordinates here, these are coordinates as if we extended the Earth's coordinate system out into space. But if we just look at the horizon at 0 and above is 90, well, there's where the top is. That's the top looking straight up, and we're going to be looking very, very close to that portion of the sky. So we're going to head there now and look at this next object, which is the result of a star that has absolutely obliterated itself. So there we go. We're heading out there, And you'll see a fuzzy little thing appear here. There it is. Right there. Yeah. This is called the Eastern Veil Nebula. And you'd be surprised, it's a supernova remnant. Now, what's going on here is that there was a supernova in this whole region, and the other half of it is out here down to the lower right somewhere. And in the middle is a black hole, and it's it's actually a pulsar, I believe. No, sorry, that's a black hole. It's Cygnus X5. And where's the location? How can we see it? Well, we can't see it because it's a black hole. But there is, if I recall, it is Cygnus X5 that makes up the remnant of this particular supernova. The supernova is huge. It's several full moons across in the sky, and it's about 1,500 light years away, and occurred about 8,000 years ago. So there were people here running around when they potentially saw this new star in the sky. It may have happened in the middle of the day, in which case it may not have been visible. But some supernovae are visible in the daytime. When Betelgeuse goes off, you'll see a second sun in the sky. Won't be as bright. It'll be a star-looking object in our sky. If you've ever seen Venus in the daytime sky, you can pick it out if you have sharp eyes. And I've showed people how to do this, and once they see it, they don't want to not look away, because then they won't see it again. They have to work at it again. But this guy here, if the supernova that happened here, we're looking at something that may have been, bright enough to be seen during the day, but not sure. It's kind of hard to predict. All right, so let's go now to our live stack. You'll see the beautiful Crescent Nebula in our buffer. Oh, that's gorgeous. That's up on our server now, and you can go grab it. Go to skytourlive.org. Scroll down, take me to cool data, and start learning how to peruse our data. And once our application gets out there, you'll be able to use our application to do all those things. It'll be direct. Look at that. That is a beautiful nebula. And what I'm going to do is minimize this. Let me just say hello here. Hunter, hi. Welcome back. My youngest coming back from work at the TV station. Okay, and then we're going to actually do this. We're going to get rid of the telescope here for a while. And let's just look at this. Look at that beautiful nebula. Look at that. And it stretches up above too. That's a stunning image, man. What do you think of that, Daryl? Looks good?
Oh, I'm going to say Joker. Somebody here said Joker the other night, and
yeah, that's right.
I saw an image of this elsewhere. Everybody goes, "Ooh, it's the Joker! Look!"
Yeah, look at that. There's that smile on the Joker.
Yeah.
There's that nose.
So I'll say Joker from now on.
Yeah. Yeah. Yeah, it's funny because after getting this camera taking pictures of this object, it doesn't look like Alfred Hitchcock anymore. It now looks like the Joker. Pretty cool. Hey, Waldo. Waldo's with us. Hey, man. Marco, hi there. Kathy, I'm doing fine. Thank you so much for asking. Yeah, this is gorgeous. This is really pretty. Look at all the filaments in here. This is supernova debris. And if you look at the lower right here, there's more. There's still more. Spock, there is more. And we have to find it. And it's going to be part of the central part of the veil. And you can see remnants up here. So this is the left side. And you can see some faint red stuff here. And then there's more stuff over in here that we're not seeing, obviously. And then to the right, way over, is the western veil. So maybe we'll image all three of those things tonight. and take you through them. So this is 25-second shot. This is really pretty. And this is 6 stacked. We'll do a stack of 8 on each of these objects so that we can look at that. Look at that. Wow. Okay, well, another thing I'll do is I'm going to activate another enhancement process called Unsharp Mask, and I'll sharpen this up. Now we can see more detail in here. Look at that. These filaments are crazy. These filaments are you know, a fraction of a light year in width and light years long. So if you were traveling in a spacecraft heading here, you might go right through them and not even know you were doing it.
Karen says it looks like the penguin because of the nose.
No.
I could almost get that too.
Yeah, me too.
That big grin, it's got to be the Joker.
Yeah. If it was the penguin, what do you mean, the Danny DeVito penguin?
Who else played the penguin?
Well, Danny DeVito, I remember that. And of course, Burgess Meredith, the original, but that's not this.
Adam West.
Adam West was Batman.
Yes, during.
Oh, you mean the Adam
Meredith
West series? Yeah.
Played the penguin during the Adam West Batman.
That's correct.
Batman.
Okay, I've already gone more than I said I would. All right, I'm going to come back here, bring this back, and let's redock this for a moment. There's 10. Okay, 10 is good, so we'll save it. Oh. Not good. I just saved it in a different location. So I have to go back and change the name, and it's going to complain because that's my fault. Okay, I'm going to say Eastern Veil. That's right, I know. Say yes, change the name. Yeah. Okay, so now we'll save it again. There we go, and then we'll save it exactly as seen. Now check this out. Check this beautiful image out. Watch this, guys. Look at that. That's what you get. That's free. Available to you at skytourlive.org. Okay, that's the Eastern Veil, rather. Did I put the wrong name in? I put the wrong name in. Okay. Oh no, I didn't. Sorry. Okay. So that's the Eastern Veil, and now what we're going to do is we're going to redock the stack here and go back to do this and take this out like this. Go back into our low light and move toward the center and pick up something that is famous called Pickering's Triangle. And I'm sure Darrow would love to tell you the story about Pickering and what happened with the real discovery of that central part of the Veil Nebula, which we're going to see here in a minute.
A lady astronomer back in the late 1800s, I think, Henrietta Swan Leavitt, discovered Pickering's Triangle. A guy named Pickering was the director of the observatory, and guess who they named Pickering's Triangle after?
Mm-hmm. Poor Henrietta.
Henrietta Leavitt was a pioneer in astronomy.
Yeah, she
Not
was.
just because she's a woman. She was an ace astronomer all in her own right.
Yeah. As was Annie Jump Cannon. Okay, so I'm going to move over a little more. As you can see, it's a pretty big object. I think this puts it in our view. I'm going to just zoom out a little bit. Yeah, okay, there it is. Okay, good. So with that right there, Pickering's Triangle is right there, but I'm going to actually head to the east a tiny bit. Okay. And go up just a little bit. And then we should have a perfect Pickering's triangle right here. Okay, that looks like it'll work. So, and what is Pickering's triangle? Well, it's just a formation made by the debris of the supernova. Now, this is stuff that's either going away from us or coming toward us, or a mixture of the two superimposed over each other. You can see a piece of it right here. All right, again, we'll do a 25-second shot and start going, and we will go into our low light view and show you the eastern veil right here. And that's beautiful, and boy is that beautiful. Yeah, okay, so we'll clear that. And now this is going to be what's called the central veil. All right, so here comes the first one of those. So check this out. Look at that. There's the central veil. Here's Pickering's triangle right there. And you drop down low. Okay, you can see the rest of it there. And that's just beautiful. I'm going to leave it a little bit to the right so we can capture some of these subtle details over here too.
Henrietta Swan Leavitt was the discoverer of the nature of Cepheid variable stars. We've talked about this before.
Yeah.
It's what Edwin Hubble used to figure out how far away Andromeda Galaxy was, and to figure out that it was actually a separate galaxy, separate from our Milky Way.
Yeah.
So, not a one-hit wonder.
No. Look at this beautiful nebula. And I mentioned Annie Jump Cannon. She was an American astronomer who actually did a lot of cataloging work, and she was really the key person who figured out how to classify stars. Now, people don't normally think of women in astronomy, but I know many women in astronomy. Tabitha Bayagian, she is someone that found that star that was fading called Tabitha's star, Tabby star. And there was evidence to suggest that maybe there was a megastructure around that star, that you saw that out there in the news, that was causing the light to dim. Could that be? Well, maybe. We often talk about how would that work, and Freeman Dyson, a famous physicist, Freeman Dyson, said that if you want to harness all the energy from your star, the best way is to encase your star in a large spherical construct so you can capture 100% or close to it of the energy of your star. Now, that's a practical impossibility, yes. However, it is something that you could see being in the realm of possibility for an advanced species. But most likely, the structural requirements of such a construct being able to hold itself together would make that impossible. So what do? Instead of doing a Dyson sphere, you do a Dyson swarm. And that is where you have hundreds of thousands, if not a million, satellites orbiting your star and capturing energy and beaming it to your planet. That would probably be microwave energy, actually, is probably the best way to transfer the energy from those satellites to your planet, a tight microwave beam. And they would be on 24/7. Satellites above the planet would receive the energy and beam it down to stations on the Earth. Could be geostationary. And if one goes out of the view, then another one picks it up, so you have a constant flood of energy into those stations. So that's a way to do it. And if you put enough satellites up there to capture energy from your star, from our perspective, we might notice that the star is dimmer, because it doesn't take much. If a tiny planet the size of the Earth, relatively speaking, that's tiny compared to, say, Jupiter, passes in front of its star as seen from the Earth, we can tell. We see that little dip, and in astronomy, one of my specialties was exoplanets, planets around other stars. So when you look at the process by which to find them, we can easily detect a dip in the star's light because a planet is getting in the front of it and blocking some of its light. And this only works if the planet is, and the system is on edge to us, so that it goes in front of its star as seen by us. If it's up here and it's going around the star like this, we can still detect it, but we have to use different methodologies. And that works out to a certain distance. So I think that's pretty cool. All right, we're at 11 here. It's one more than I wanted to, but that's okay. There's Central Veil and Pickering's Triangle.
Change the name.
I did. It's Central Veil.
Oh.
Yeah. Thanks. So the triangle we're looking at is right here. Okay. Here's the triangle. Okay. And in between. So that's actually Pickering's Triangle. And it's actually a really beautiful part of the nebula. Like I said, that stuff can be going away from us or coming toward us or both. It's probably a combination of the two, because that's the central part. So we imagine a supernova spreading spherically out into space around the star. So some of that stuff coming toward us here might be also in the view of the stuff going away from us over there. So even though that stuff is spreading away and it is moving, some of it we could check and see if any of the lines in this material show any Doppler shift, so that we see spectral lines. When we see color like this, we get emission lines, and if any of the emission lines are off, we can tell which direction it's moving by looking at which way they're shifted. If they're shifted toward the red, it's moving away from us, red shift. If it's shifted toward the blue, it's moving toward us, blue shift. And so we could check by looking at the spectral features and detect just which way this is going and which parts of it are going. There's been studies of this. Now we're going to go and check out the object that's down here at the bottom, that is just off the bottom view here. And it's right down there. You can start to see the little edge of it. I zoomed way out so you can see it. Okay. All right. So we'll just save this one more time. Central Veil. Save exactly as seen. There we go. Now we're going to go see the other item to show the rest of this massive, unbelievable supernova remnant. And let's go to our low light mode. And we'll see right now that our low light mode is right there. Okay. Oh, look at that. I believe we had some wind. You just saw that moving. Look at, see the wind? It's causing the stars to go wonky a little bit. So the desert winds have started up, but not a problem. We can reject them. All right, so we're now going to go to this next part of the nebula, and this will show you a rough view of what the whole thing looks like. Okay, so we are in the central veil here. Okay, that's where our telescope is pointing right there. And we're going to go down to this guy right here. All right. I'll take us to 52 Cygni. And as I drop down, you'll see a star come into the view. You can't see the nebula too well right now, but you'll see the star.
when we saw the nebula in its entirety in Stellarium a moment ago. You can see the face at the top, triangle close to center, and then this part, it called it the Filamentary Nebula, on the far side, on the other side from the face. This is the western veil, and when you see the entire nebula, you can see this with the filter in the eyepiece of a telescope, an O3 filter. The entire nebula is like 3 degrees across, or about 6 lunar diameters.
And when he talks about O3 filter, he's talking about oxygen and the Roman numeral 3. What's that? That's a doubly ionized oxygen atom. Gives off that bluish green glow that we see right here. Okay. Now that bluish green glow is actually created by 2 electrons leaving the oxygen atom out in deep space in this cloud. And as I've said before, it stands to reason that we'd see oxygen in the universe a lot, because oxygen is the 3rd most abundant element in the entire universe. When we look at elemental abundances in the universe, oxygen is really high, and the 4th most abundant is carbon, that from which we are made. So I'm convinced it's a carbon life-based universe. I'm pretty convinced of that. All right, so here is this right here. This is called a witch's broom. It goes larger than our field here, but what we're going to do is we're going to do another 25-second shot, and you'll see now the other side of the nebula moving out the other way, the opposite direction as the previous shots, rather the eastern veil shot. That's 52 Cygni. That's actually a star in our foreground. So here's the central veil, our leftover from the last one. It's in our image buffer, and that's a piece of this nebula that we're shooting right now. All right, so we'll clear this. It'll be up on our skytourlive.org site. Again, you can join there if you want. You can join our Patreon. Ah, look at that. That's beautiful, Daryl.
Yeah.
You can see the bottom of Pickering's triangle here, and more detail, which is why I left this a little to the right so you can see the stuff down here. 52 Cygni is up here in the foreground, and that nebula is way back here. So it's not involved with this nebula at all. Okay, let's color correct. You'll notice the curves change position each time a photo is taken, and that's because of the fact that we're finding that as we take these pictures, okay, the image gets refined, and what's happening is we're actually stacking. We're taking one image, then taking a second image, aligning it with the first so all the stars match up, and then putting it on top. And we keep doing that over and over, making an image sandwich, as I always say. And that image sandwich, the thicker the sandwich, the cleaner the image looks, the less noise, digital noise, that we see. Each individual photo is got a lot of noise in it, but when you stack them together, the random noise averages out to an average background. So we will see that we won't have a lot of noise back here. If we zoom in right now, with only 4 shots done, okay, I mean 4 shots is actually pretty good. You'll see that we have this modeling. That's noise. These filaments aren't very well defined yet, but as we keep going, we'll do this later and you'll see that they get much more well defined. Hey C&D boy, what's going up? What's going up with you? I think your name is you're Doug, aren't you? I'm trying to remember. There we go. Look at that color. Color correction shows well. Our red, green, and blue curves here. Yeah. Hey, and Prowl's with us. Hi, Prowl. Our red, green, and blue curves here are all lined up, and this is the average of the intensity of the curves right here, the white one, and that's the one that we work with, right? So if we go just to the left of that peak, that's about as dark as we can get the image without losing data. And this is our mid-range, and using this one we actually do what's called a push. We can push this way and see hidden data. So you see we've got subtle data over here that disappears, subtle data over here, and as we go back to our previous position, some of that data retreats a little bit into the background, and we do that on purpose just to try and get this to look pretty noise-free throughout the whole process. Ron Regier, hey, thanks for coming, man. You've been up since 5 in the morning, huh? Wow. Well, hey, thank you for coming by. It was great to see you, Ron. I will make it up to Rimrock to say hi to you at some point. That's a promise. So have a good evening, sir. Keith Evans, how you doing, man? You're just in time to see the Western Veil. Very nice. Now we've had some wind, and you can see that I've got a threshold of 8.08. Now that's literally a pixel percentage. We don't want to have oblate stars or stars that show wind damage, because then you'd find that you had long lines for your stars and dashes. I want round stars. See, 9.01. Telescope's being moved around out there by wind, and this filters out those things. I'm actually going to drop this down from 8 to just about, well, 8.08 to about 8. So we're going to make it even more stringent, and then it'll start to get better, and we'll start getting green here in just a bit as the wind starts to die down. And there we go.
Mark, would you excuse me a moment, please?
Absolutely. See ya. I'll be
right
here.
back.
I'll wait for you right here. Thanks, Keith. Thank you for saying that. He says that's beautiful. Yeah. It's good to see it too. C&D. James Hyde's with us. Hey, man. How are you? Straight Tail Adventures. I like that. Can you tell us about Straight Tail Adventures, James? Prowl says the blue is so vibrant, amazing. Yeah, that's as we've talked about, the doubly ionized oxygen that we see in supernova remnants. And I mentioned before that, oxygen is, again, the third most abundant element in the universe, so it stands to reason that it would be made in stars that end up going supernova. Or it's also the stars were made with it, and massive amounts of it, because they were made from other material that was made in the hearts of stars before, including hydrogen, helium, oxygen, carbon, and then the stars themselves make more of that stuff. So it's an interesting chemical factory that the stars are, in their very nature. Cosmic Ray, hey there. James Hyde says, Straight Tail Adventures. Oh, that's what you meant. Oh, very cool. He says his YouTube channel. Check his channel out, guys. Straight Tail Adventures. The channel of him flying his 1958 Straight Tail Cessna. But the tornado in 21 took it. Oh man. I'm sorry to hear that. Beautiful vintage aircraft. Sorry to hear that, James. Okay, we're gonna save our Western Veil here before I forget. Okay, save exactly as seen. Oh, very good. Oh. And C&D says that the solar storms are messing up signals and so forth up in Canada, where he's from. But the auroras were cool. Yeah, that's neat. Nice. James says, yeah, we were lucky. Other people lost more than we did. All he did was lose his plane. That's a vintage investment, though. But, well, thanks for telling us about that, James. That was really cool. Make sure you check out his channel, Straight Tail Adventures. That's neat. Alright. We'll go to 12 on this, and then we'll be done with the veil. There we go. Did we get a 12th? Yes, we did. 12 images stacked will make a relatively noise-free image, so that's really good. And then we'll save it exactly as seen. Alright. Then I'll show you the image you're going to get. If you go up to skytourlive.org, okay, then this is the image that's waiting for you up there. It'll be there in probably less than 30 seconds. We've been trying to refine our processes, make sure they all work. And we're pretty happy with how things are working right now. Okay. So we'll come out of here and go to our low light mode. You'll see in the live view, when we don't have anything stacking, you'll see the stars dance around a little bit, and that's from the problem when they actually get hit by wind in this long barrel, which acts like a weather vane. It's like a flag. Okay, let's go back here. Yeah, see, you just seen it move. Come out of here a little bit. And let's come back this way. We've done this. I want to check something out over here, maybe that. Let's back out a little. Yeah. This is pretty high up as well.
Closer to the lizard.
Yeah. And right near Lacerda the Lizard is the Cocoon Nebula. And we will go there, because we've been looking at star death tonight, and I think I'd like to show you star birth. So we'll go to Lacerda. You'll see our crosshair for STLS end up right in there. There it is. And we can see the stars. We also see this dark area. I'm trying to find.
Lubo in China has a question for you.
Okay, what's he asking? I'm going to try and do this here.
What mount are you using? Are you auto-guiding?
Oh, to answer your question, yes, we are auto-guiding, and I'm using the mount that is, there we are. I'm using a mount that came with a telescope. It's a fork mount. I can actually show you that real quick. Alright, so here you see the telescope right here. Let me move it up for you. Okay, there's one side of the fork, there's the other side of the fork. There's the telescope, and the camera's in here, and we're looking at a guide scope on the far side. You can't see it here. This is the bottom of the telescope here. we see counterweights on the bottom here. So you can't really see too much at this particular vantage point, but I'll show that to you a little bit later. All right, let me get this down here.
Interesting. My Meade equatorial mount, go-to mount I bought nearly 30 years ago, was also called an LX. Mine was an LXD 600, I believe.
Okay.
That was the German equatorial mount of the day. It was a go-to mount, early one, and had slot car motors in it.
Oh, wow.
Things sounded like a coffee grinder when it ran.
Yeah, that's still what happens with the Meade instruments. They actually still sound like coffee grinders. I got people saying they like the sound of the motors, and they'd like to have me put a sound microphone in the observatory, which I think is great. Okay, so there's the cocoon. All right, and now that we know it's here, you can see a little bit of rough nebula here, and then it goes up and out. So we're going to do a 25-second shot of this. It's rare that I've taken a photo of this with this new camera. The old camera could not see the detail this one sees, so that's right off the bat a better thing. But this is a stellar nursery, and so we've gone from seeing the death of stars to the birth of stars. This is the death of stars, very, very colorful, very pretty, but also these are nebulae of doom because you could never survive in them. And these emission nebulae that you're about to see are the nebula that are emitting light just like the ones we just saw, but they're emitting light of stars that have just been born. Look at that beautiful nebula and the stars inside that are ionizing the hydrogen gas that's within this dark cloud that you see trailing off like a comet. Okay, that star is ionizing the hydrogen in this cloud out to a certain distance, beyond which it can't do it anymore. And so that's why it drops off. There's an ionization radius that occurs. And again, it's mostly hydrogen, but as we see as it sharpens up here, we're going to see that some of the dust is scattering some of the blue light from the star and making what's called a reflection nebula, a blue light nebula. And we have to be careful because the blue of those reflection nebulae sometimes is confused for the oxygen, the ionized oxygen nebulae, but they're two different things created two very different ways. All right.
So we've kind of gone full circle here from the death of little stars to death of big stars and
To the birth.
to the birth of stars.
Exactly. Hey, Cosmic Flow, how you doing?
As I said on Battlestar Galactica, the reboot, this has all happened before and it shall all happen again.
Lubo, thanks for your question earlier, by the way. Hey, Cosmic Flow, thank you. Yeah, it is a beautiful nebula. It almost looks like a comet, a nebula comet, right? Now, as we are taking more exposures, we notice also that we have 5 shots we've taken right here, and none were rejected. Confirmed, of course, with our full width half maximum filter, and it's down in the 6s. So I'm going to lower this down to just above that threshold, so we can actually make sure that we stay with just beautiful round stars here. And this will be the last object for tonight. We started with star death tonight, and we're ending with star birth. So you see the full cycle of the universe. And as far as life on Earth and where it came from, I've said before, we were made in the dark. Life began in the dark, and so we see life that is created in the darkness because it's created in these dark nebulae. Probably in a nebula like this at some point. And then as the stars migrated out, they didn't ionize the hydrogen anymore, and we ended up seeing a lot of independent stars that moved away from their source birthplace, like here in this nebula. Now you can see a little bit of the blue starting to show through here. Around this star we have a blue cloud. That blue nebula is a reflection nebula. The blue is caused by the particles of dust, which this is all dust in here. These aren't voids in the stars. This is dust up here blocking all the stars back here. And so we see this star sending out its light, and the dust is scattering some of its blue light. Okay, let's see if we can bring some of this in a little bit more. I'm going to take this just to the left of the peak. There we go. And now you can see some more blue out here. I'm also going to come into the enhancement and turn off the mask to just give it a little better color rendering for us at the moment. And there you go. Check that out. Now you see that the dark dust in this whole nebula region is scattering some of the star's blue light, making a sort of a bluish nebula. And where there's a very heavy concentration of hydrogen, you see that the star is ionizing the hydrogen gas and making it glow red, which dominates over the reflected light, the dimmer scattered or reflected light we see, like around this star and stuff. Really neat. And out here, this is a very, very dense region of stars. This dark dust is blocking what's behind them. Yeah, look at that. That's incredible. Yeah. Yeah, we see such beautiful detail with this camera that we just couldn't see before. Look at that. That's really nice. Lubo has another question. He says, does the USA get more auroras reaching down further south because of geomagnetic poles actually in Canada? I have no luck with aurora location here in China, in my location. Certainly the geomagnetic north does play a major role. So we might see a lopsided auroral oval, yes, because it is following the geomagnetic pole. It's not following the actual physical pole. It's following the magnetic pole. So yeah, we'll see an increase. But to that end, Lubo, don't feel bad. We don't get a whole lot of auroras down this far in Connecticut, where I am, and I'm in the northern U.S. relatively. And here in Arizona, where this is all, we had one night where we had auroras seen in this observatory, and this is the southwest of the United States. And on that night, you probably could have seen auroras in China. Of course, I don't know where you are in China. Tell me where you are in China. What's that?
Auroras were visible in Arizona a day or two ago.
If they were, then I'll have them on the all-sky, so I'll be able to find them. Lady Astrid's with us. How are you? I'm glad you're new. Thank you so much for liking us. Did you subscribe? All our photographs that we take are free at skytourlive.org. You can take down just tons of beautiful images that we've taken over the last year and a half. Or 2 years, I'm sorry, 2.5 years. So feel free. We also could use help in the Patreon. You could go to skytourlive.org and donate if you wanted to, one time or a lot of times. You can donate to the Patreon or be part of the Patreon and get some really cool stuff on a monthly basis. And we're working on setting up people who join the Patreon get like mugs and things like that. And I'm talking to our organization partners to see if we can do that. We certainly can do that. Let me start by saying that, and I want to do that. So, and we also have equipment giveaways here, courtesy of Tiffany Echo and Michael Tarr. They get equipment, and we're their exclusive giveaway partners. And we give away binoculars, whole telescopes, and eventually we want to give away a night vision system or more that I think are really, really going to get people hyped. There's nothing like taking a pair of binoculars out, laying down on the ground, looking up at the pair of binoculars, and seeing the universe like you've never seen it before. And that's what we're all about. That's what we're doing here. See this? That's something you've never seen before. This is the cocoon.
Karen,
yeah, go ahead.
Karen Belmont had a question I'd like to expand on a bit.
Sure, read it first, though.
Yeah, well, see, she's almost out of view now. Would love to know where the comet will appear this fall. I gave her a short answer in chat, but everybody should know this. Folks, Comet Tsuchinshan Atlas will be appearing possibly as soon as already tonight, more likely in the next day or two. It's going to start out low in the west-southwest after sunset. You might start looking about, take a look at 15 minutes after sunset. You'll see Venus very bright over rather low in the west-southwest. And the comet should appear to the right of Venus. Now, at first, if you don't see it in 15 minutes, check again at 30 minutes and again at 45 minutes. Hopefully you will see something. Early on in this evening apparition, the comet is going to be pretty low, but it's going to be climbing higher each night. It may peak on about the 14th. It's hard to say. They're hoping for a great tail to be on display now, and the entire comet to be much brighter because of forward scattering of sunlight and the angle of the dangle between us, the comet, and the sun. The comet just passed between the Earth and the sun. One, you'll want a low western horizon. The lower the better. Two, if you really want to see the comet well, you need to get away from city lights. Would certainly help. I'm on the east side of Colorado Springs, and I'm looking across the entire light dome of the city, which is over 500,000 people now. And if I want to get a really good look, I'd have to go an hour or more west of town here, up in the mountains, to get a really good look at it. It was in the morning sky, but it's now moving to the evening sky. So look west, southwest. That's a little south of west. After sunset, starting about 15 minutes after sunset. Check again 30 minutes after and 45 minutes after. And you made me amazed at what you see. Thank you.
No, that's great, Daryl. Thank you.
And
We'll try to view it ourselves, but I mean, we're going to have a moon to contend with.
Yeah, that's a problem too. We're hoping for a great comet to appear in the skies. We haven't had a really great comet.
Neowise is great.
Neowise. Last great comet I saw was Hale-Bopp back in the late 90s.
I mean, with your eyes, you saw Neowise with us, but I know what you're talking about.
Yes.
Let's just pull out of this just a little bit, and then let's actually use our course adjustment histogram here to kind of draw a little more detail out and see what else is in here. This gives us a rough idea of what we're looking at in here. Now you can see the filamentary structure in this black material. Really, really awesome. And then at the end of it is this little stellar nursery. So as we've talked about, we've gone from star death to star life. And no, stars aren't alive in the truest sense of the word, but they wink into existence when fusion can commence in the core of this compressed hydrogen ball that is caused by a mutual gravitational contraction of a cloud of hydrogen gas. And that temperature has to reach 10 million Celsius for this process to commence. And then we can get hydrogen fusion. Hydrogen atoms being compressed and forming helium in the core of the star. And these aren't atoms, these are nuclei of atoms. So one proton and another proton. No, that's a hydrogen proton. They smash together, and there's a whole bunch of intermediate steps that we won't go into, but in the end, they form an isotope of helium. And it's actually an isotope of hydrogen, which forms an isotope of helium. Isotopes are just atomic nuclei that have additional neutrons in the nucleus. Okay, so hydrogen, an hydrogen atom, okay, a proton with an electron with one neutron, which has no charge, in the center, adds mass, but we call that deuterium, right? And if you add a second proton, a second neutron into the nucleus of the atom, then we have tritium. See? So this is in the fusion process, we use deuterium. There's deuterium. The stars use deuterium. All right, and they form a helium isotope, and that helium isotope is what we call the helium ash, or the result of the fusion process. Now, on Sunday nights, we have a radio show called SkyTour Radio, and that's on from 6 p.m. to 8 p.m. Eastern Time in the U.S. It's out of Ogden, Utah, with KGRA. On YouTube, it's kgradb.com. And we talk about things like the process by which all this happens. We go into a little bit of more detail that we don't go into here. And I mentioned that all the different processes, like for those stars we saw in before, the star that went supernova, when it made hydrogen into helium initially, it used a whole different process. It didn't use the same process that our sun uses to do hydrogen fusion. It used one that involves carbon, nitrogen, and oxygen. We know this as the CNO cycle. And those more massive stars will use that, and that's the primary method for making hydrogen into helium in these bigger stars. And there's a whole number of ways we can go. Did you say the isotopes are a baseball team?
Oh, come on. The Simpsons, you know?
Oh, I'm not a
The
Simpson.
Isotopes are the name of the baseball team in Springfield in The Simpsons.
I'm sorry, I didn't know that. I don't watch The Simpsons.
Well, I haven't watched Simpsons in 20 years probably, but I still know that.
Well, I've never watched it, so I don't know that. I've watched it, you know. It just never grabbed me like Family Guy grabbed me. Family Guy was funnier.
Yeah.
Woohoo! Nobody saw me do it. Can't prove a thing. I know some of the taglines, but that's about it.
I wore a Bart Simpson Don't Have a Cowman t-shirt.
Oh, yeah, that's right.
When I was in Germany in 1990, and Europe hadn't been exposed to The Simpsons yet, and boy, I got some weird looks from people.
I did get a t-shirt, by the way. It just come out of the wash today. and it has the NASA blue ball on it of the Earth. Okay, and it says, "Not flat. We checked." So I'm looking forward to wearing that. Yeah, this is pretty. Look at that. Let's move this over.
It's nice.
Yeah, so now you guys, you can see there's more texture in here. And now that we have 41 pictures all stacked on top of each other, we can see now a lot more detail in here. And now, if I come in and I add the enhancement, it'll add a little more noise, but you'll see more detail in all these filaments. Look at that. Now we see lots of detail. And one way to actually manage this detail is to drop this guy down just a little bit. Like that. And now we see the same amount of detail, just a little softer, a little more balanced. Looks really pretty. And there's some of that blue nebula mixed in with the dark. You know. Now here's a relatively dark spot. Let's increase the brightness here just to see what we're looking at in that dark spot. So we come up here, and when we look at this area, this looks like a round or spherical gravitationally condensing area. I think that's pretty cool. Lubo in China says, is there a theoretical star so massive as it would not let light escape but would not yet become a black hole? Oh, I see what you mean. No, the difference between a black hole and any star is literally an immense yawning, gaping wide chasm of gravitational strength over distance. Okay, you can figure what's called the Schwarzschild radius of a black hole, and that radius is generally measured in kilometers. Okay, and the diameters of stars are measured in hundreds of thousands of kilometers, or even over 1 million kilometers or more, several million. So black holes are very, very small, relatively speaking. So we wouldn't see a star ever acting like a black hole. And think it through. If a star was acting like a black hole, we wouldn't know it was there, would we? Light wouldn't escape it. Nice.
Django, there is a rather odd thing they think happens with some black holes, though. There are like millisecond pulsars that are spinning so fast that that's the only thing, the centrifugal force outwards is the only thing keeping that pulsar from collapsing and becoming a black hole. And sometimes they do, because millisecond pulsars slow down. And it's like skating on very thin ice, where ultimately that super fast neutron star is going to cross the line and slow down just enough that it's suddenly going to collapse into a black hole. So they say.
Yeah. Okay, we're gonna try and get the maximum darkness here by going to the right to the peak.
Wow. Ray says observed magnitude of the comet is minus 4.9, which is brighter than Venus.
Well, that's an overall magnitude. It'll look dimmer to the eye.
You're no fun.
I would like to, if it's up there, I'd like to check it out.
Sure. It was cloudy here tonight.
Mm-hmm. Okay, we're gonna go here to Cocoon. We're going to save it at 50 images. If you if you go to my Facebook site, guys, you'll see I will sometimes take some of these images like this one here. Okay, look at that. It looks like a streaking comet. I'll take some of these images and I'll actually do the hyper processing to really make it look beautiful, and I'll upload it to show you what you can get if you be part of our Patreon if you want to join us. But I hope you guys had a good time tonight. We are going to call it for tonight. Tonight was a Star Birth and Star Death, Star Death and Star Birth a stream to kind of show you the way things look when they are born and where they look when they die. So I hope you enjoyed that. But we will be back. Oh gosh, and as the moon gets fuller, we tend to stop streaming around the gibbous moon. We'll go right through first quarter to just before gibbous, which is the 3/4 full. And once it's full, we don't stream, and once it's gibbous, we don't stream. We stay away from the full moon because we end up getting a very bright image, even with our filters, and we want to avoid that as best we can. But this image will be up on the server, skytourlive.org. Please consider donating. Go there, you can donate. Please consider joining our Patreon. We have a number of Patreon people that have joined us and part of us, but we would love it if you would consider becoming a Patreon member, because it's the only way that we can keep doing this. And so far, we're running right on the line, but I don't get paid. Daryl doesn't get paid. Marianne doesn't get paid. Tara doesn't get paid. None of us get paid. But you get the benefit of seeing all this. So if you find it's a value, consider a one-time donation or what have you. And I hate doing this. I feel like I'm begging. But then again, I watch public radio and public television. And that's all they do is beg. And it's like I feel like they have no shame. But we're providing something I think that is valuable. Long-distance astronomical and astronomy education, which is something that just there isn't enough of. We've lost this in our schools, and people come here and they say, wow, I didn't even know these things were there. Wow. Yeah. Anyway, you guys have a good night, and check out skytourlive.org. Scroll down, check the whole site out, check it out. We have a Patreon segment. We have a SkyTour radio location. You can go see the radio show, and it's a video radio show too, so you actually can see and hear us as well. And you can actually check out the pictures. We have galleries. We have all these images here. All the evening images are on our server. Enjoy them. Follow the instructions, and you can get there. You have any questions? You can always email me, and my email is mufonanalyst@gmail.com. Okay, that's my email. You can get me there. You can also get me at ContactSkyTour@gmail.com as well. So your call. You guys have a good night, and we will see you on the next clear night.
Good night, everybody.
Good night, folks. Come again. Bye-bye.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe near. Real-time wonders to see, streaming live for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the view. unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real like a gleam. Lift your eye up so high, across the stars beyond the sky. Sky Tour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. Sky Tour is bringing the views, every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky Tour is bringing the view,